Hello everyone and welcome to my September presentation. I'm Alireza Alizadeh and this is CS Internship. In this presentation we're going to go through all the technical details and the stuff that was included in this step material, and we're going to summarize it more in terms of idea rather than technical, mathematical and scientific details. So the first part was a continuation of your data types, basically. The different data types that you have and how you're going to store your data when programming. So you were introduced to lists, tuples, sets, and dictionaries. This is basically the ultimate cheat sheet for your programming if you're dealing with these kind of data types. You can see their initializers and how you can define each one and their properties, basically. Can they be nested? Can they be duplicate? To have duplicate elements or not? And you will realize that the representation of sets and dictionaries is the same. And that's because the data that we store in them are different, and that's how we can make the differentiation. That's how different they are. Sets are just a bunch of data, bunch of numbers that are not duplicated. They're unique, but dictionaries have a key value kind of dynamic. So you have a key and a value assigned to it. So that's the basic difference between these two and how we can differentiate them even though they have the same presentation. Other than that is the idea that they are mutable, immutable, and how you can, change them if you can change them. So you have here that a set is mutable. You can change it, but you have to be careful to not change, or add a duplicate element. So if you have 1 and 2 in your set, you can't have another 1. This is not going to happen. Other than that, dictionaries are mutable. Tuples are immutable. So once you define them, that's what it is. You have to work with that. And lists, as we all know, are mutable. Then we have the idea that if they're ordered or not ordered, tuples are ordered, lists are ordered, sets are unordered, and dictionaries are ordered if you're using a modern Python version, i.e. 3.7 or above. After that, we have a little bit of an example here of how to, use these data types. And the only cool thing here is that if you're doing a if you're doing a tuple, because tuples are defined like this, so 1, 2, and etc. If you just want a tuple with one element, so you don't want the 2, you just want this as a tuple, you can't do this basically because this would register as an integer. So this would be an int. You have to either do a set beforehand, or if you don't want to do a set beforehand, include a comma. And that will basically make it to a tuple. Tuple, not set. I used the wrong initializer for that. Here you can see all the elements and all the examples. Moving on from this, you have strings, and they are immutable, but they have all these different methods that sometimes change our strings. So imagine this. You have a string like x, and it's hi or hello. You can use a method like capitalize to make all of your letters uppercase. So if they're immutable, how are we doing this? The idea is that you have your words in your memory and they're stored here, right? This is your word, okay? This is your Hello. Although they're immutable, they're subscriptable, which means you can go through them. So basically what we do is go through this immutable string that we have. So we go through it and say, okay, I have an H, and I go somewhere else in my memory and say, okay, have an uppercase one and have an uppercase one of the next one. so on and so forth. And then we change the reference to x to point to this memory instead of the previous one. So that's basically all about the strings and how they are immutable. The other stuff are just tools. It's good to have all of these in your repertoire, the same way that it's good to have all of these data types in your repertoire. If you can learn to store your data properly, you can then work with it a lot easier. Big problem that you might face in analyzing a data set is that the data is simply not stored properly. After that, we're going to talk about flow controls, which are conditional statements that you have here: if, else, if, elif, and so on and so forth. Then you have transfer statements. So basically, if you have a block of code and you put a break, what do? You have a break here. You stop and exit that block of code and go to your main program that you have. That's what a break does. Continue basically means continue, and pass is a skip, which means if you're in a loop, for example. So imagine this. You have a loop that's going and you have a condition somewhere in here. So for example, you have an if condition in the middle, and if x happens, pass, which means don't do the rest of the loop, just loop back to the beginning and start again. Skip that, iteration of your loop if you want to rephrase it a bit. Here we have a bit of an example of how flow controls work, and it's a practical example. It's for solving an AI problem, a constraint satisfaction problem, is CSP for short. And since the material for this step included classes, I also included an example that requires a class. So to summarize classes, they are a capsule for your data. A lot of languages have structs, which are a bit simpler. They are basically a capsule of data. So you have like a list here, and you have some ints, and so on and so forth. But in a class, you have the option to have some functions and methods as well. So a class has some functions as well. And that's basically class. Look at it as a encapsulation of data that is related to each other. And you can see here a flow control of solving an AI problem, which is a never-ending loop unless one of these conditions are meted. So you have a while true, which basically means the program comes here. Okay, I'm going to do this. Okay, does this happen? Exit. If not, I'm going to circle back to the top and do this loop over and over and over again until I meet one of these conditions or run out of a tree, because this loop works on a tree that has a bunch of children and a root. And if you go through all of the tree, there's nothing else to analyze anymore. So you don't need to continue and you return your answer. And that's a very practical example because it's an actual problem of tracking some chipped animals with a bunch of sensors. So imagine you're running a zoo or a conservation center or something like that. You have a sanctuary. You have animals that are chipped. You need to know their locations. This is the code that does all that work. So after this, we are in a different realm, sort of. It's still mathematics. Programming is still mathematics, but this is linear algebra and some abstract algebra on top of that. And the first thing that you're going to get used to working and you're going to get introduced to is a system of linear equations. What is a linear equation? The same equations that we've seen in high school like this, but here, to work with them, we transfer them into matrices. So this would eventually, if you want to work with it, become this. 4, another 4, you have a 2 and a -4. And then you would have your x's, So x1 and x2, and all of this basically is going to equal to 5 and 1. So this is, let's say this is your matrix A, which is just take these little guys here and turn them into a matrix. These are your variables that you want to find, and or x, we denote that x, and this is B. So how many solutions do they have? Well, if you look at the visual representation of a linear system of linear equations, you basically have 3 different scenarios. So either 2 lines that you have are like this, they don't meet, so you have 0 solutions, or they are like the picture and they meet in one place or more than, in some cases more than one place. But if it's one place, then you have 1, and if they have multiple, so for example, if you have something like this, it's gonna have multiple answers. So, and generally we like to say it's either none, 1, or infinite. So you have these ideas. Another example of infinite would be if they were like this. Imagine this. You have this line and you have another line on top of it. That system of linear equations has infinite possibilities for answers. Moving on from that a bit, how do you find the solutions? Where, if you remember our notations and how we name them, you basically, for the particular solutions, that is just the answer to this particular problem that you want to know what x values you need to meet these 5 and 1, you do this and just solve that, and that's your particular solution. If you want to find all the solutions, you solve this. You solve for 0 and you get all the solutions. To get a general solution for this problem, you combine these 2 parts, which is not a big deal. Like, imagine you have a set of numbers here and another set of numbers somewhere else, and you're gonna say, okay, this has some, coverage of the other one, so it's gonna be like all this part here, like minus some bits in the middle. So it's not a weird thing to do. But the interesting fact is the particular solution, which is this, and the general solutions, which particular solution is a part of, are not unique. So you and your friend could use 2 different methods and use different decompositions for your matrices and have different answers, which are all valid. So keep that in mind. It's good to know. If you want to work a bit easier, you have to work a bit harder. So what do I mean by that? So you have A, which is your matrix, you have your variables, and you have what you want to achieve, B. If you want to have an easier time solving these, what you want to do is basically transform your matrix to an easier form. So if you swap 2 rows of your matrix and you swap them, it's okay. That's not going to change your answer. If you multiply it by a non-zero value, so you multiply this by 2 and then add it to this one, these are all valid. These are not going to change your solution. But if you achieve some forms like row echelon form or a triangular form, it's going to make your life easier, because your data for the first variable that you're trying to find just has one possibility. So it's going to make it easier for you to solve your equations. Other than that, it's the Gaussian elimination, which is basically doing the same things that I mentioned about the rows and achieving a row echelon form. We have a reduced row echelon form, which is basically a row echelon form, but instead, in each column, you only have the leftmost value is only 1, and in that column, in each row, the leftmost value is 1, and other than that, you in that column you just have zeros. You don't have any other data. This helps us to calculate inverse of a matrix, which can be a hard thing to do if you don't know how to do this, because you're gonna do well with 2 by 2, 3 by 3s, but after that it's gonna be a hell of a lot harder. So if you basically do a matrix, an identity matrix next to it, and try to move these around in a way that identity matrix is to the left, what is left to the right is gonna be the inverse of your original matrix. So there's that. Groups are part of abstract algebra. They're very simple. You have a binary operation, which we denote with this. You have a set of data, and if all of these conditions apply, you have a group. You have infinite, space to do whatever you want as long as you adhere to these conditions. After that, we have the idea of linear independence. Basically means, can you define or describe a vector, which we have here, with other vectors? So in case of this one, the blue one here, you can't with these two other vectors. But the black one is a linear combination of these two. This is a very simple idea, and mathematical details are left up to you. And the last thing that we're gonna talk about, or second to last thing, is norms. Norms are lengths. It's very simple. You have a vector, and you wanna know its lengths. So lengths of v. A physical manifestation of a norm is your measuring tape, or is your ruler that you use in real life. That's a Euclidean metric, and it's the metric that we use in books and stuff, unless it's mentioned otherwise. Most books use it as the metric to measure stuff. So if you ever see a ruler, that's a physical manifestation of this idea. The last thing that we're going to talk about is inner products, orthogonal and orthonormals, projections. Orthogonality, basically, the visual representation is this. You have a vector here, you have a vector here. If the angle between them is 90, then they are orthogonal. If the length of each vector is 1, then they are orthonormal. One thing that you might note is that another way to describe this is if the inner product of two vectors is 0, but we have multiple inner products, and you don't need all of them to be 0. So two vectors can be orthogonal in respect to one inner product and not in respect to other inner products. Other than that, we have the idea of projection, which is, visually speaking, is very simple. For example, imagine this. I have this line here, right? And I have a bunch of data here. If I want to do an orthogonal projection, which means basically a 90-degree angle from this data point to my line, right? So if I come down here, okay, this is gonna be its projection. And that's all we had to say. I didn't get to go into details that much, but that's basically all of the ideas. It's better to know ideas and have them as tools in your repertoire, and rather than get very deep technically on what they mean mathematically, because if you do that, sometimes it takes away the ability of the listener to be creative with your tools, because they're so focused on the scientific definition of it. And that's all, folks. Thanks for listening, and thanks for watching.